We have a car of 800 kilograms, and that pulls a trailer of mass 200 kilograms, and it's using a tow bar to do so. We're told resistances to motion. So for the car, it's 400 newtons. So let's say the whole thing's moving to the right. The resistive force opposes the motion. So for the car, it'll be 400 newtons towards the left. And then for the trailer, it'll be 200 newtons towards the left as well. And then we're told the driving force on the car. So there's a forward force on the car of 1200 newtons. And the first two parts of the question are to work out the acceleration and the tension in the tow bar. The tensions in the tow bar will act in these directions. There's T and there's T for the car. So as you can imagine, as this whole system accelerates towards the right, there must be a force on this object that pulls it in that direction, or that gives it a resultant force in that direction, and that will be the tension in the tow bar. And for the car, the trailer will pull it backwards, and that's why the tension is towards the left. And this is our acceleration. So to work out the acceleration, probably the easiest way to do that is to consider the car and the trailer as one system, or as one object. So here is the car plus the trailer. The overall weight is 1,000 kilograms. Acceleration still towards the right. The driving force on the whole system is 1,200 newtons. And the overall backwards force is going to be 600 towards the left. The tension forces are an internal force, and whenever you have an internal force, they cancel out. So that would not be represented on our diagram. So now we can consider the overall force towards the right. The resultant force will be 1,200 minus 600 towards the right, and that will be equal to ma. That will be equal to 1,000 times the acceleration. So 600 is equal to 1,000 times acceleration. Acceleration is then 600 over 1,000, which is then 0.6 meters per second squared. So that is part A done. And for part B, where we're trying to work out the tension in the tow bar, so now that we have our acceleration, let's alter our diagram. So this is now 0.6, as is this. We want to work out tension. We're no longer going to consider the two masses as one single mass. We're going to look at them separately, as when we look at them separately, that's when we have the tension forces coming into play. There is no tension force in this scenario, so there's no point considering it as one single object. So we can either look at the trailer, or we can look at the car. I think the trailer would be better, because the car has 3 forces, the trailer just has 2. So it's a bit simpler with the trailer, but to be honest, it doesn't really make much difference. If you were to consider the trailer or the car, you'll end up with the same final answer for tension. The only difference is when you consider the car, you just have one extra force to deal with. So for the trailer, there is a force of T towards the right, and there is a force of 200 towards the left. So therefore the overall force to the right, or the resultant force, will be T minus 200. And that's equal to the trailer's mass multiplied by the acceleration. So T minus 200 is equal to 120, and then we end up with T is equal to 320 newtons. And now for part C, final part. So we're told that there's a hazard ahead, and then we said the force from the engine is reduced to 0 and the brakes are applied. So let's redraw our force diagram. There is no more forwards driving force, so we can get rid of that. The braking force on the car is F newtons, so that'll be towards the left. That slows down the car. And it says that the resistances to motion are unchanged. So there is still a resistance force of 400 newtons on the car, and there is a resistance force of 200 newtons on the trailer. We're told that the thrust in the tow bar is 100 newtons. Thrust acts in the opposite direction to tension, so if the tension was this way, the thrust will be the other way, this way and this way. So as you can imagine, as the car is moving forwards and it brakes, If it weren't for this tow bar, then the trailer would crash into the back of the car. So the tow bar pushes the trailer towards the left to stop it from crashing into the back of the car. And if that's happening, if the trailer is effectively being pushed into the back of the car as the car is braking, well, that's why this thrust force will be towards the right. It pushes into the back of the car. So that's our force diagram. We know that the thrust force is 100 newtons, so I'm going to change these two T's to 100. And it's decelerating, the system, so we know that the acceleration will point in this direction, which I'm going to call A. It doesn't have to be the same acceleration as before, so we're not going to call it 0.6. So, again, we have three options. We can consider just the trailer, just the car, or the system as a whole. Our goal is to work out F. If we look at the trailer, we know all of the forces on the trailer. So that's a good starting point. The trailer experiences an overall force towards the left of 300 newtons. We know the acceleration is towards the left. We know that this has a mass of 200 kilograms. So then using F is equal to ma, the overall force is 300, the mass is 200, the acceleration is a will then be 300 over 200, or 1.5 meters per second squared. So now we have the deceleration, or the acceleration towards the left. And now we're trying to work out what F is, so we can look at this object. So for that object, so remember that the acceleration is towards the left, that means the resultant force is that way. So the overall resultant force will be F plus 400, that's the force towards the left, minus the force in the opposite direction to acceleration, so minus 100, and that will be equal to ma, so that will be equal to 800 times 1.5. Let's simplify, so F plus 300 is then equal to 800 times 1.5, which is 1200. F is then equal to 900 newtons, and that is our answer.